We've mostly seen Taylor series in a more theoretical context, but I want to point out in this video some different applications that we can use Taylor series for. And two of those are going to be limits and definite integrals. So to start with, let's look at an example involving a limit. So if we're asked to use Taylor series to evaluate the limit as x approaches 0 of 1 minus cosine of x all divided by x squared. Now, in trying to find this limit, if I were to plug in x equals 0, what's significant is I would get 0 divided by 0. Now, that is an indeterminate form, and we could avoid using Taylor series if we just used L'Hopital's rule. But there's something nice about the approach we'll go through here, and in particular, if we didn't know that the function in the top was 1 minus cosine of x, but we did have information about its Taylor polynomial, we would still be able to evaluate it the way we'll see here, but not necessarily using L'Hopital's rule because we have to really have some information about that function. So what we want to start with is remembering what the Taylor series for cosine of x is. So cosine of x, we said, had Taylor series, which was the sum from 0 to infinity of negative 1 to the k, x raised to the 2k divided by 2k factorial. And significantly, that had the radius of convergence equal to infinity. So the interval was the whole real line. So we could sum the series for any x in there by equating it to cosine of x. For our purposes, what I want to note is the first several terms of this. When you plug in k equals 0, you get positive 1, and then we would get minus x squared over 2 factorial plus x to the 4th over 4 factorial, and so on. So it's using really these terms written out that I could say if I want to find the limit as x approaches 0 of 1 minus cosine of x all over x squared, that should be equivalent to replacing cosine with its Taylor series centered at 0. Oops, this is an x. So instead of writing that in sigma notation, I'm going to write out term-wise what we have up here. And one thing to note is that I now have 1 on the outside and I'm subtracting the 1 on the inside. So we can get rid of that. And then the other thing I want to make sure I do is distribute my minus sign in through the parentheses. So this now becomes equivalent to the limit as x approaches 0 of positive x squared over 2 minus x to the 4th over 4 factorial and so on. And this is still x squared. The significance now of having gotten rid of the constant 1 is that every term in the numerator has a power of x that's 2 or greater. So what I can really do is just cancel the x squared in the denominator with an x squared factor from all of the terms in the numerator. So this would become the limit as x approaches 0 of 1/2 minus x squared over 4 factorial, etc. And importantly, everything after that plus sign with the ellipses there would involve some power of x. And in fact, we know it would be greater than 2. The reason that's significant is that when I start to plug in x equals 0 at this point, everything after this dotted line would evaluate to 0 because there's still an x term in there. Consequently, we would be able to know that our limit would evaluate to the value 1/2. So we're taking advantage of having effectively even just the Taylor polynomial centered at 0 because we really were interested in the first several terms of that. So we can use the nice properties of these polynomials to help us evaluate certain limits. Maybe an even more striking example of their utility is dealing with integration, because we've seen that there exist things that we can't integrate, come up with an antiderivative in terms of elementary functions, or even sometimes we've encountered things that we could, but maybe it was very complicated to integrate them. So you can imagine a situation where you need to evaluate a definite integral within some level of accuracy, but not necessarily that you need the exact value of that. That's where Taylor series can be really helpful. So use Taylor series to approximate the integral from 0 to 1/2 of the function 1 over 1 plus x to the 7th to within 10 raised to the negative 7th. So, like I said, the key thing here is that this is an integrand that we do not know how to come up with an antiderivative for. So using FTC directly with that is not something that's feasible. But this is prompting us to use Taylor series. So my start here is that I want to write the integrand as a Taylor series. Now we get to choose the center. Notice that one of the points here of my integral is 0, so it makes sense for me to talk about expressing this as the Taylor series centered at 0. So to do so, we can practice what we have learned about using old Taylor series to create new ones. So the function 1 over 1 plus x to the 7th, what is striking to me is its similarity to the function 1 over 1 minus x, and we have a Taylor series centered at 0 for that. So I'm going to note the connection that this is the same thing as 1 minus negative x to the 7th. Then if I consult my known Taylor series for 1 over 1 minus x, I'm going to take, that would have had terms x to the k, but now I take that negative x to the 7th and write that to the k. Now, one of the other things we've stressed is the importance of simplifying before we move on. So the first thing I want to do after that is express this as negative 1 to the k, x raised to the 7k. So this is a Taylor series representation for the integrand, what I've boxed in red there. So that means that if we go back to the task of trying to evaluate the integral, I can say the integral from 0 to 1/2 of 1 over 1 plus x to the 7th is equal to the integral from 0 to 1/2 of its Taylor series, which we found in the line above. And at this point, it's important that we have already discussed how to integrate power series. We primarily just looked at indefinite integrals, but we saw how to find the antiderivative. Of course, one big difference is we put in a plus c in the previous cases, but because this is a definite integral, we won't have to do that. So the antiderivative of this is, again, you want to focus on only the parts that involve x, so not getting kind of bogged down by these k's. So negative 1 to the k is constant with respect to x. But x to the 7k now becomes x to the 7k plus 1, and we have to bring a 7k plus 1 down here. So that's kind of reversing the power rule. This is the antiderivative, and we are evaluating this from x equals 0 to x equals 1/2. Now, just like we've seen with FTC in the past, when I want to evaluate my integral, I need to plug in the top bound and subtract what I get when I plug in the bottom bound. But notice the significance here of that lower limit. If I plug in x equals 0, that effectively is going to be the sum of 0. So that lower limit would actually give me 0. So consequently, I don't end up having a difference of two sums. Instead, I really just have the sum that I get from this top bound. And that is the sum from k equals 0 to infinity of negative 1 raised to the k times 1/2 raised to the 7k plus 1 over 7k plus 1. So if we pause here, what I want to point out is that this is exactly equal to the integral from 0 to 1/2 of 1 over 1 plus x to the 7th. So if we could evaluate the sum of this series, we would have the exact answer to this integral. Of course, I don't know the sum of that series, but also I'm not asked to find the exact value. What we want to do is approximate this integral. So notice that that translates now to approximating this infinite series. And in particular, we'd like to approximate it so that we have a small enough error. So this now comes back to our notion of error bounds. I'll point out here that while this is a Taylor series, we are not asked to use Taylor's remainder theorem. And instead, I'm really just looking at this as how can we approximate an infinite sum using its nth partial sum and guarantee that we have enough terms to make that error small enough. So what we can think about here is we need to decide how large n should be in order to obtain the desired level of accuracy, which was 10 to the negative 7th here. So one key thing that I'll point out is that if you look at this series that we're trying to approximate, it's an alternating series. And the significance of that is that for alternating series, we know that the alternating series test provides an error bound for us. So for alternating series, we know that this error is bounded above by the absolute value of the next term. So it suffices here for us to focus on this and try to make that smaller than 10 to the negative 7th. So we need to find n so that a sub n plus 1 in absolute value is smaller than 10 to the negative 7th. And when I'm talking about a sub n plus 1, note that this that I have in the blue box is a sub k. So I'm interpreting that as my general term. We want to consider when the absolute value of that, such that I plug in n plus 1 in place of k, is smaller than 10 to the negative 7th. So if I go back up to what I have in blue, replace every k with an n plus 1, that becomes the absolute value of negative 1 raised to the n plus 1 times 1/2 raised to the 7 times n plus 1 plus 1 divided by 7 times n plus 1 plus 1. Now we can clean that up a little bit. The absolute value tells us we can disregard the negative 1, and I can write this as 1/2 to the 7n plus 8 divided by 7n plus 8. And so this gives us a very concrete inequality to deal with. So at this point, what we could do is plug in values of n to see when we get something smaller than 10 to the negative 7th. So for instance, you could check that n equals 2 works. And what I'd like to do is just kind of bring this back to the significance of what that means. This means that if we come back to the problem at hand, in approximating the original integral, by finding that n equals 2 satisfies the inequality in the end, that means that I can take the sum, which was exactly equal to the integral, and simply stop after the n equals 2 term. So putting that into practice here, this means that the integral from 0 to 1/2 of 1 over 1 plus x to the 7th is, first of all, we said it's exactly equal to the infinite sum that we found. And we decided that we could approximate that infinite sum by the sum where we stop at k equals 2. So that looks like, again, this. Now, one thing I'll point out is because this sum starts at k equals 0, even though we have n equals 2, this will result in 3 terms. The k equals 0 term, the k equals 1 term, and the k equals 2 term. And again, I should be careful that this is approximated. So these two sums are not equal. And we're saying then that this is approximately the first 3 terms. So 1/2 minus 1 over 8 times 2 to the 8th plus 1 over 15 times 2 to the 15th. And so this number that I'm ending up with here is an approximation of the definite integral. And what we know is that it is close enough to the true answer such that the difference between what I have boxed in red and the original integral has to be smaller than 10 to the negative 7th. So we would have the assurance that we were really, really close. And if for whatever application we were using this, if 10 to the negative 7th was good enough, then it wouldn't matter that I don't know how to integrate this exactly. So this gives me a nice way to approximate it, and I can also decide on how accurate I need to be.